Hi, this video is about using the Universal Gravitation Equation. Now, in previous videos, I've discussed how the force of gravity is related to the masses of two objects and the separation distance between their two centers. And this is true for any two objects in the universe, according to Isaac Newton. All objects attract each other. But just how much force are we talking here? Because in everyday ordinary objects, I don't see them orbiting around each other, right? I don't see the whole world revolving around me. Maybe you do see it revolving around yourself. But in most cases, I don't see objects attracting each other gravitationally. So we must be talking about a pretty low force. How much force are we talking here? Because if we use this relationship here, you'll notice this is kind of a weird symbol. This is not an equal sign, but a proportional sign. The force of gravity is proportional to the masses of the two objects, and the distance between those two objects is inversely proportional to the distance squared. But I wonder if we put in actual numbers here for the masses in kilograms and the distance in meters, that's not going to give us a measurement in newtons, which is the force that we want. If we did try that, we would get units for kilograms, it would be kilograms times kilograms, and the units for distance would be meters squared. And the units for newtons units for the force is newtons. These two units do not equal each other, and that's a problem in physics. We want the units on each side of the equation to balance out. Now I'm going to simplify this a little bit. I'm going to combine these kilograms into just kilograms squared on the top here. So we want units of newtons. That means we need to introduce some kind of conversion factor here that would give us units of newtons, so that we could have an equal sign between these two quantities here. The only way that's possible is if we have a unit that cancels out the kilogram squared and the meter squared. And so we need to basically undo those. And I'm going to cancel out the kilogram squared by putting that on the bottom, and then the meter squared by putting that on the top. Our conversion factor is going to have these units, but how much do we need here? How much is the gravitational force in newtons between two ordinary objects like this? And we know the answer because of some experiments done in the history of science. The Cavendish experiment is famously the first experiment that tried to measure the gravitational force between two ordinary objects on Earth. And it takes very sensitive equipment to do this. But after doing these tests, they found that this unit here is a very small number, this conversion factor. It's 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. This quantity right here is known as the universal gravitation constant, because this is what gravity is equal to, this strength anywhere in the universe. This is the universal gravitational constant, and we use capital G to represent this quantity. So this is the key to making this equation up here into an actual equation. So what we can do is we can translate this proportional relationship into finally an actual equation using this G factor here. And everything else stays the same. We just have this conversion factor, the universal gravitational constant. So this is the universal gravitation equation. And this was originally developed by Isaac Newton. And this value of G is 6.67 times 10 to the negative 11. So I'd like to show you how we can work some word problems with this equation. So what if we wanted to find the gravitational attraction between the Earth and the Moon? So what we would need to do is we need to check a table of data for the masses of the Earth and the Moon and the average distance between them. So let me do that. All right, so I've done some research. I've found the mass of the Earth to be 5.97 times 10 to the 24 kilograms. The mass of the Moon is 7.35 times 10 to the 22 kilograms. Their average distance is 3.84 times 10 to the 8 meters. And what I'm going to look for is the force of gravity between them. So this is the equation I'm going to use. Now that I know all of these other quantities here, I can solve for the force of gravity. So I'm going to just quickly do that right here. The force of gravity is equal to, and then I'm going to have a lot of numbers here that I'm going to write in. So I'll fast forward. All right, so I've substituted all my values in. I have 6.67 times 10 to the negative 11 for big G here, universal gravitational constant. Got the mass of the Earth, mass of the Moon. You'll notice I used the little E symbol instead of writing out times 10 to the power of. This is an abbreviation you can use for exponential, the scientific notation, and you can use this in your calculator as well. Don't forget to square the distance here when you're doing these kind of problems. So now that I've done all this, I can do a little bit of math. I'm going to multiply these two numbers in the numerator together, and then I'm going to divide by first I'm going to square this number here. All right, so I've done some math in the numerator and the denominator. Now I'm ready to multiply the numerator by this gravitational constant over here, which is all over 1. So I can multiply the numerators and the denominators together just to make it a little bit more simplified. All right, so I've done that. I realized that I had the units over here flipped, so I fixed the units over here. So when I did that, the kilograms squared canceled out right here, and it left me with just newtons times meters squared on the top. I got this number when I multiplied 6.67 times 10 to the negative 11 by 4.39 times 10 to the 47. So I'm left with this, and now I can just divide these two numbers right here, and the meters squared cancel out. It leaves me with newtons, which is what I would like for a force. And so my force here is 1.98 times 10 to the 20 newtons. So that is the average gravitational force between the Earth and the Moon. So let's do another one. What if we just had two ordinary objects? The gravitational force between them should be pretty small. So what if we had a backpack, a 3.35 kilogram backpack full of books, and it is 65 centimeters away from a 12 kilogram desk? So what would the gravitational force between these two be? Now, right off the bat, I see centimeters. I know that I need to change that into meters. So I'm going to divide by 100 to get that into meters. The mass of the first object is 3.35 kilograms. The mass of the second object is 12.0 kilograms. And we want to know what is the gravitational force between them. So we're going to use the same equation. This time the numbers will start out a little bit smaller. So we're using this equation again. We still have the same gravitational constant each time. And I like to always write out the units because I want to show that the units always work out in the end. Of course, when you're doing this yourself, you can take shortcuts at your own risk. But shortcuts make long delays, so just be careful about that. And don't forget to square the distance at the bottom. So after putting in all my numbers into this equation, I can multiply. I'm going to multiply the 3.35 and the 12 together, and I'm just going to go ahead and multiply this as well. So doing that gives me 2.68 times 10 to the negative 9 newtons times meters squared on my numerator. And then in the denominator, I have 0.4225. I'm going to wait to round. So now I can divide these two. The meters squared cancel out. And so that leaves me with a gravitational force of 6.35 times 10 to the negative 9 newtons. That is an extremely weak force. So weak, in fact, that you would not notice a gravitational force between a backpack and a desk. So that's all I've got for you in this video. Remember, this day could be your last, so live on purpose.